Into the unknown, into the unknown, into the unknown. Ugh. I'll work on it. I won't work on it. You know I'm not going to work on it. I just like driving you, you know, sad. Not sad. I don't want you to be sad. I just like being annoying sometimes. You get it. Anyway, how many grams of iron metal are needed to completely react with 4.35 moles of oxygen gas? Last video, we did a problem where the given was grams and the unknown was moles, and now we're gonna do it backwards. So this problem here, and then I told you I would skip to the next video. Well, now it's the next video, so now we're gonna do it. We this time have a given of moles and an unknown of grams, and we're gonna have to convert that. But if you look closely, you'll see that your given is one chemical, oxygen, and your unknown is a different chemical, iron. When you are changing chemicals, the only way you can do that is with the mole bridge. And if you're going to use the mole bridge, that means you need the coefficients in the reaction put into your conversion fraction. So our given is oxygen gas. So I'm going to put a little dot here to remind myself that's where I'm starting. My unknown is iron metal. I'm going to go from my given into the unknown, right there. Ta-da. And I know that whatever my given is, I need to start with that. I know that if I have both grams and moles, that's gonna be a two-step or two-fraction problem. That's true whether we're talking about the given being grams and the unknown being moles, or if the given is moles and the unknown is grams. Either way, that's still a two-step or two-fraction problem. So you can even just like right away, as soon as you see that this is a problem with moles and grams, you can go ahead and draw your two fractions there. Remember, what goes up must come down. So moles of O2 have to come down to the bottom. Remember, your unknown goes on top at the end. So now that there's a second fraction, the end is that second fraction, and your unknown's got to go way over there. Way over there. And so that means too, when you're trying to figure out where your conversion for your mole bridge is going to go, remember that the mole bridge is for moles only. It's called a mole bridge because it is for moles only. Only moles can go on that thing. Quit trying to put it where grams are. You cannot put the mole bridge anywhere where there's grams. That is a lie. You cannot do it. Okay. It's not allowed. They will tell you to take your grams and go back to Canada. So your mole bridge has to go on this only fraction that does not have grams. That's the only one it can go on. That fraction doesn't have any freaking grams on it. You cannot put it somewhere that has grams. You can only put it where moles are. So knowing that this is the only fraction where the bridge can even go, because that's the only fraction with no grams, if you know that, then that means you can put your given and unknown on this fraction. You know that your mole bridge fraction should always be given on the bottom and unknown on top, because that's how we convert. So we go from our given into the unknown, which in this case is iron. Our unknown, right, was the iron, moles of iron. I know it has to be moles here because, again, like, the unknown was iron, and I cannot put grams on a fraction where the bridge is. That's not allowed. You're doing it wrong. So you got to do moles of iron because the bridge has to be moles. It is a mole bridge. It's not a freaking gram bridge. It's a mole bridge. So you got to put moles there. Okay. What numbers of moles are you going to use? That would be the coefficients from the reaction. So this 3 and this 4 from the reaction, 3 for moles of O2 and 4 for moles of iron. To finish filling out your final fraction of your conversion, do what goes up must come down again. These moles of iron are on top. They need to come down to the bottom. What goes up must come down. And that means this fraction is back to our like kicking it old school style of needing like your number of moles to always be 1, and your grams come from the periodic table. So if your number of moles is always 1, whoops, I just pressed a button I didn't mean to press. If your number of moles is always 1, I did it again. Okay, there, I think I got it. Okay. Then you put a 1 in there. Your grams come from the periodic table, which for iron is 55.85. And then you can put this in a calculator. You know that whatever is on top gets multiplied and whatever is on bottom gets divided. And you also know that you don't need to put times 1 or divided by 1 in a calculator because that's not going to change anything. So 4.35 times 4 times 55.85 divided by 3 is 323.93 grams of iron. It's really kind of simple. It's fine. Like, there's nothing special about it that we haven't already seen before. That's pretty much all there is to it. I'm going to do one more problem like that where the given is moles and the unknown is grams. And then we're going to do something else that's more complicated because that's how we roll. Number 3 down here, your given is moles of oxygen and your unknown is grams of water. So again, I know I'm going to start with the given always. If I notice that my given is moles and my unknown is grams, that actually tells me I'm going to need 2 fractions. This is a 2-step problem. And I know that what goes up must come down. So I'm going to put moles of O2 on the bottom of the next fraction. I know that whatever the unknown is goes on top at the end. So grams of water is the unknown that goes on top at the end. And I know that if I am changing chemicals, I have oxygen and water. I am changing chemicals. Anytime that I'm changing chemicals, I can only do that if I have the mole bridge. I cannot change chemicals unless I have a mole bridge. So now I need to decide, where does the mole bridge go? And there's only one place where I can put the mole bridge. That mole bridge has to go on this fraction because it cannot go on the final fraction. It's not allowed to go there. You know why? Because it's not a freaking gram bridge. Okay, you cannot put the mole bridge at the end because it's not a freaking gram bridge. The only place for it to go is this middle of the problem fraction. So we know that the mole bridge goes from the bottom to the top of the fraction, which means from the given on the bottom to the unknown on the top. So that's going to be the unknown is water on top. But since it is a mole bridge, even though the final answer needs to be grams of water for your unknown, this is a mole bridge. So in the mole bridge, you have to put moles of water. And then we also know what goes up must come down. So on the bottom of the final fraction, moles of water are going to show up there again. For your mole bridge fraction, the numbers of moles come from the bridge, which means from the reaction. So my given was the 5O2 in the reaction. My unknown was the 4H2O in the reaction. Remember that any of these coefficients here, even if they're invisible, the coefficients in the reaction are numbers of moles. That reaction that says 1 C3H5, that's 1 mole of C3H5. They didn't even write the 1, but we know when they don't write a number, it's implied 1. Then 5 moles of O2 yields 3 moles of CO2 plus 4 moles of H2O. We know that's what that reaction actually means. So when we do 5 moles of O2 and 4 moles of water, we see that in the reaction, that's also going to be 5 moles of O2 in our fraction and 4 moles of water in our fraction. And then for the final conversion that's between moles and grams, that's a fraction like what we used to do before, in the before times in our moles pre-Stoich unit, which means that your number of moles will just be 1. and your number of grams needs to come from the periodic table. So H2O, we need the molar mass. There's 2 hydrogens and 1 oxygen. And when you add that up, it comes out to 18.016 grams of water for every 1 mole of oxygen, or for every 1 mole of water. So we have our given. We did what goes up must come down. We put our unknown on top at the end. And we used our mole bridge to convert. And we used 1 mole in the periodic table for grams to convert. And then at the end, when you actually stick this in a calculator, 8 times 4 times 18.016 on top, and then divide by the bottom. So that's divided by 5. We don't have to put the divided by 1 in there because we know it's not actually going to change anything. Round to the 100th place, and you get 115.30 grams of water. It's time to move on. Are you ready for this? It's going to be pretty exciting because when you go to the next page, we can also do conversions in stoichiometry where we start with grams and end with grams. Dun, 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 dun. Grams everywhere. Okay. We had previously talked about like how many steps and how many fractions for when you are given and unknown moles and moles, or when you're given and unknown are moles and grams. If your given is grams and your unknown is grams, if it is grams and grams, guess what, my friends? That is a 3-step problem. You're gonna need 3 fractions. So like here, how many grams of nickel metal is my unknown? Needed to completely react with 23.5 grams of oxygen gas. That's my given. That means, and you're going to want to start writing like all the way as far left as your paper goes. That's just a pro tip. You're going to run out of room otherwise. That means your 23.5 grams of oxygen goes at the beginning because that's your given. But then you're going to need 3 fractions to do the work. You do what goes up must come down, right? Grams of oxygen. You know that your unknown grams of nickel must go on top at the end. That is still true. We have more fractions now, but it still goes on top at the end. That has not changed. And that means your mole bridge has to go in the only fraction that does not have grams, because it's not a freaking gram bridge. So you cannot put the mole bridge here, and you cannot put the mole bridge here. It cannot go in the first fraction or the 3rd fraction because those fractions have grams. You only have 1 fraction that does not have grams. That is the only place where your mole bridge can go because it's not a freaking gram bridge, okay? Remember, your mole bridge goes from the given moles on bottom to the unknown moles on top. So the given moles this time is oxygen and the unknown is nickel. And then your numbers for that mole bridge come from the reaction. So your given oxygen to your unknown nickel into the unknown, it's 3 oxygen and it's 4 nickel. So from there, trying to fill in these other spots and these other fractions, we like did the easy parts first, right? But you know, what goes up must come down. We'll bring moles of nickel down to the bottom of the final fraction. And if you're thinking about it, you also know that like this moles of oxygen on the bottom of your mole bridge fraction had to come from somewhere. And if what goes up must come down, then moles of oxygen should have been on top of the 2nd fraction. Because what goes up must come down. And we already know from the mole bridge, the moles of oxygen has to be down at the bottom there. So it also started at the top here. To fill in these fractions with moles and grams, those are our old school style mole fractions. So the number of moles is 1 for both of those. And then your grams come from the periodic table. So for O2, that's 16 times 2 is 32.00 grams. And then if you check nickel on the periodic table, 58.69. Nice. All right. You filled in all your fractions. Okay. And that means we just got to calculate it. So 23.5 on top. You don't need to put the times 1 in the calculator because you know it's not going to change anything. But times 4 and times 58.69, and then divide by the 32 on the bottom, divide by the 3 on the bottom. You don't have to divide by 1 because you know it's not going to change anything. Round to the hundredths place. If you type this correctly in your own calculator, you should have gotten 57.47 grams of nickel. And there you go. That's a gram, whoops, stoichiometry problem, where you start with grams of one chemical, change it to moles of that chemical, change it to moles of a different chemical, change it to grams of the second chemical, and then you end with grams of your second species. That's it. They're all of the gram problems look like this.